So let's look at a very important operation on matrices, which is called as determinants. Now this is an extremely important operation on a matrix. So I'll roughly tell you what happens. So we'll discuss about the operation in detail anyways in the determinants chapter. But for now, what I would like to tell you is you have a matrix A. You pass it through this process called taking its determinant. So what you get as your output is some number called k, which can be real or complex. So every matrix can be associated with this real or complex number k through this process of finding its determinant. So what happens is, first of all, determinants are only valid for square matrices. Remember this point, extremely important. If the matrix is not a square matrix, forget about the term called determinants for it. There is no determinant for which exists for such a square matrix. So it is valid only for a square matrix. Next, the next thing that I want you to understand right now is you take a matrix, you find its determinant. What you get in return, or what you get as your final answer, has to be some real or complex number. So you have converted a matrix into some number, some number called k, and that is what I mean by finding its determinant. So we'll look into the process of finding the determinant in detail anyways in the chapter determinants, and we'll also leave a link for you to see that yourself. For now, what I would like to tell is, if you have a matrix A, right, like something like this, A, B, C, D, I'm not showing you how to find its determinant, but I'm telling you its determinant is denoted like this, mod A, det A, that's how it's called. Det A is equal to determinant of A, B, C, D. So the only difference here is, this is a determinant, and this sort of a bracket is called matrix, right? So remember this denotation. Now, we are not at all touching into how to find determinants right now. We are leaving it at this thing. We'll just see a couple of properties which we will anyways see in the determinants chapter again, but anyways I'm just putting it across right now, so that you, even if you just look at them right now, when you read that chapter again, you'll anyways recollect them and you'll be able to understand better. So it goes like this: if A1, A2, so on, An are your matrices, are all square matrices, then the determinant of their product. So also remember, we'll anyways see how, when are two matrices eligible to be multiplied and when they are not, right? So there is a condition that has to be followed, only then they'll be eligible to be multiplied. So assuming that all of these are following that condition, right, assuming that all of these are following this condition, and then we've been able to multiply them successfully, and we've got a product matrix, and we are taking the determinant of that product matrix, right? So that's what is happening here. This will be equal to the product of their individual determinants, the product of their individual determinants, right? That's what I'm trying to say. The determinant of the product is the product of the determinants, right? That is what is the first property I wanted to remember. The second property being, if k is a scalar, then determinant of ka is equals to k power n into determinant of a, where where n is the order, where n, yes, rub and write this again, where n is the order of the matrix A. Now, so what's happening here is, you are taking a matrix A, which is obviously a square matrix, only then we are talking about determinants. If it was not a square matrix, there was no point talking about determinants at all. You have taken the square matrix whose order is n. What do you mean by order being n? It means n cross n. There are n rows and n columns, right? That's what it means. So you have taken that matrix, you have multiplied it with k. That means every data of this matrix is multiplied with k, right? That is what this particular thing means. And now you have taken the determinant of that. So that is what this means, this part. This will be equal to k power n into determinant of a, right? So you take the determinant of a and just multiply with k power n, where n is the order, right? So again, we are not discussing the proof as such in detail, but I would just like to give an idea as to how this is happening. For example, you have 1, 2, 3, 4, something like this. So it's very easy to find its determinant. Again, I'm not explained you how to find it, but I will just tell you here, like there's nothing wrong. 4 minus 6, which is minus 2, right? Now if I multiply 2 to this, right? This is your a. How about 2a? So 2a will be like this: 2, 4, 6 and 8. And now I'm taking the determinant of this. So what will happen is, that will be 2 into 8. So 2 into 8 minus 6 into 4, which means it is 2 into 1 into 2 into 4 minus 2 into 3 into 2 into 2, right? So what's happening here is 1 into 4, and here also you're having a 1 into 4, just that 2 is multiplied to both, right? And that's how you do it, right? You take a product and take a minus sign and take this product, right? Something like that. So you have a 3 into 2 here, but each of them is multiplied to 2. So the order of the matrix will determine how many times this scalar is multiplied, right? So here, as you can see, because the order was 2 here, 2 by 2, it is multiplied twice. That's why you can take 2 square common, and then you'll have a 1 into 4 minus 3 into 2. And this 1 into 4 and minus 1 into 4 minus 3 into 2 is the determinant of a only. So that's why it's 2 square into a, right? So basically 2 was your scalar, which is your k, and this 2 is the order, which is your n, right? Which is 2 in this case. So that's why 2 power 2. So I just took this example to make you understand as to how this is happening. But anyways, it's a result worth remembering, and I will only put results in front of you which are worth remembering. So this one is, you might get a direct question on this, and this is also pretty easy to remember, right? I'm not proving this right now because proving this is not that simple, so I'm just leaving it here. But proving this intuitively, at least with the help of an example, is pretty simple, so that's why I did that. But anyways, we'll look into how to find a determinant in detail when we come across the chapter called determinants. So with this, for now, as far as this chapter is concerned, we've finished the subtopic called determinants. So let's proceed.